Okay, our next keynote is going to be Microchip, and we have two executives from Microchip that will be speaking. There'll be Kyle Gady, he's Associate Director of Microchip's Data Center Segment Group. He's been with Microchip for nearly 25 years, and before his current position, Kyle was Field Application Manager and a Principal Manager. He holds a Bachelor of Science degree in Electrical Engineering from the University of Texas, Austin. And Rob Reed, who is Senior Director of Product Development Engineering for Data Center Solution Group for Microchip. He's responsible for managing and designing the storage silicon. And prior to that role, Rob was VP of Data Center SSD Engineering at Kioxia, responsible for the design and launch of Kioxia's first data center Gen 4 PCIe BiCS4 SSD. You learned from a previous presentation that's bit cost scalable for NAND flash memory. And Rob also worked at Intel as product development manager for solid state drive products. He has expertise in engineering management, silicon architecture, product development, strategic planning, and application engineering. He holds 6 patents in the US on SSD storage, and Rob holds a bachelor's honors degree in electronics and communication engineering from the University of Huddersfield University. And the talk today is going to be quantum-proofing AI, next-gen security for protecting the world's data. Please join me in welcoming Kyle and Rob.
All right. Thank you so much, Jay, for that introduction. So this is Kyle Gady, as Jay introduced. So I'm Rob Reed, the Senior Director of Product Development for Microchip. And what that really means is, we are creating and delivering storage solutions, and that's kind of what my team does. So silicon, firmware, validation, everything, software, and we do boards, and also the full solution. Today we're going to talk about quantum-proofing AI for next-generation security. What does that really mean? We're going to discuss some of the areas that we think are driving this. Kyle is going to discuss some of the ingredients and some of the techniques that we need to execute on this for the future. So before we get going, I just wanted to talk a little bit about Microchip technology. So Microchip prides itself with being smart, connected, and secure in everything that it does when it delivers products to its customers. Microchip was founded in 1989, and through 19 acquisitions to this point, Microchip has grown into a large company with about 22,000 employees through the leadership of Steve Sanghi in the early days and now Ganesh Murthy. And for Microchip, employees are really Microchip's greatest strength. So we take pride in our employees at Microchip. Our revenue last year was around $7.6 billion. And we really take IP seriously and technology seriously, and we have about 14,000 patents worldwide. So what does it mean for Microchip to deliver a system solution? So Microchip is really about empowering innovation. And the way we do that, we look at the megatrends in the industry, and we've identified 7 megatrends. There's 5G, there's sustainability, which I think is on everybody's minds as we look around the world today. Definitely something that's important for us to look at. IoT and edge computing, e-mobility, and more autonomous driving. But the one that we're going to focus on is data center. And of those 6, the 7th that pulls everything together, which is this new phenomenon around AI and ML, which is impacting every single one of those megatrends. And so at Microchip, we then break that down into 6 different markets of communications, consumer appliance, industrial, aerospace and defense, and also automotive. And for us today, we're really going to auger in on the data center and computing market segment. So connecting, managing, and securing the data. So for storage, we have our NVMe SSD controllers, which our 5th generation was announced yesterday, which contains a hardware root of trust and also a machine learning engine, so we can implement some of these security usages that Kyle is going to touch on later. We also have our CXL memory products, where we are demoing with Micron, a great partner of ours, our CXL memory usage. And we also have our switching products to connect and secure servers and GPUs. Our purpose is really to rapidly innovate with deep collaboration to drive a sustainable evolution of the data center. So to set up the conversation that Kyle's going to cover, we broke down the cloud infrastructure, and we broke it into 3 fairly simple areas. So we have the cloud, the traditional cloud. We have the edge with servers, and now AI servers. And now we have the far edge, and the far edge is continuously changing and adopting and moving to meet the new demands of today's markets. And we see that's more like a micro data center. You can think of it like a micro data center that's highly modular, and it contains things like CXL memory expanders, CPUs, storage cards, of course NVMe SSDs to accelerate performance at the far edge, and then some kind of security, and then obviously a network. On the edge, we have traditional servers, and then we have AI servers. And on the AI servers, we're really focused on PCIe switches for connectivity, and then there's GPU modules in there. Again, NVMe SSDs for performance, and of course, networking. And then on the cloud, we have optical transport networking and Ethernet, and timing and synchronization. So why do I have this slide up here? Why am I going through each little piece? Is because we fundamentally believe that each little piece needs to be secure. Because how do we know the data coming from the server is trusted? How do we know the data in the memory is trusted? So that's really the core of what we're going to talk about today, and Kyle will cover more details. So as I look at the data protection required, why do we need to do this, okay? We identified just 4 of the top areas that we consider the major attack vectors that I'm sure everyone in the audience has experienced at one point or another. Especially, we call it system and human errors. And that's when you get the email that says, such an account, your credit card has expired, you need to click on this link and fill in your credit card, your social security number, et cetera, et cetera. And these scams are becoming more and more sophisticated with AI. There are also voice activated AI scams where you'll get a call and you'll think it's a loved one on the other end of the phone, and someone is going to demand a ransom or some money or something of that nature. And these are real cases that have been in the news recently. We also see those can be a cause of a cyber attack. Usually the cyber attack is to glean money or information that's deemed valuable so a ransom or money can be obtained. And just recently, we're seeing a lot of these AI fake social media accounts being generated, which are also used for nefarious reasons. In today's presentation, though, Kyle is really going to look at physical attacks and supply chain attacks. So physical attacks, this could be the vandalism of a system. This could be someone taking down the power network in an entire state or country. And these can be highly, highly disruptive and to many, many people worldwide. There's also theft of property. There's equipment out there that's very expensive and can be stolen with these physical attacks. And then the last one is really the supply chain attack. So on the supply chain, there have been cases where the air conditioning vendor has been hacked because the target is over here and they really want to get the information from the target, so they hack the air conditioning vendor. Then they go in the back door with the air conditioning vendor and they either send the data out immediately from the target or they send it back to the third party and then they send it out from the third party. And that's how these supply chain hacks and attacks are happening. So with that, I'm going to hand it over to Kyle, and he can explain to you some of the ingredients and requirements we need to combat these attacks. Thank you, Kyle.
Thank you, Rob. Hi, my name is Kyle Gady. I lead our data center market segment group for Microchip. First, I thought I'd start with a story. This takes me all the way back to my days in college, the University of Texas at Austin. I was leading the computer lab data center in housing and food, and one day we decided to start a new server. And this server was using a new emerging operating system at the time, Linux. And of course, we didn't have the modern software deployment systems that we have today, where we could easily update the system and get the latest software downloaded onto the machine from the internet. This system was deployed using a CD-ROM that we had laying around at the office. And of course, once we got that machine loaded up, we ran some tests, we did some configuration, everything looked okay, and we forgot about it. It was sitting in the corner of the room, unused for a while. One day we got a call from another institution, and they said, "We're seeing an attack on our network, and it's coming from your computer in your lab." I knew immediately. Panic set in. Immediately, I knew which computer it was. I walked over to that computer, pulled the network cable, unplugged it. Thankfully, I could do that with that system, and luckily, nothing ever came of it. But we did anxiously await any news that would come about where we might end up in the news and on a slide like this in the future. Thankfully, I don't today have to do deployment of these types of security systems for our company. We do have security experts who have contributed to this presentation, and I want to thank them. I'll expand on a couple of points that Rob just mentioned. So Rob talked about the importance of protection in a distributed environment. We see today that there's devices on the edge that are joining the network all the time. We have AI systems coming online near the edge devices in local computing environments, things like hospitals, airports. All of these systems are there to enhance our lives and make our jobs easier and more productive. But at the same time, this distributed network creates a larger attack surface for nefarious actors to come in and steal valuable data and equipment. In fact, a recent article was talking about the costs of these attacks and the surface that it presents. A recent IBM research report said that the cost of cyber attacks is now approaching $5 million per incident, and that 1 in 3 of these incidents involves what's called shadow data. Now, what is shadow data? Shadow data is present on your network where you need resiliency. You have copies of this data, could be in a public cloud, could be at a private cloud, could be at an airport, could be in a closet somewhere. This data creates a challenge for anyone implementing security because it creates a very large surface of attack. One of the recommendations from that article is to manage the inventory of equipment on your network And we're going to talk a little bit more about how you can do that. But the answer is not to take all these systems, collect them up, put them into one place, and guard it like Fort Knox. We need these systems out there, real time, running inference on the edge. We need these systems in our hands and the tools readily available. We will become more and more dependent on these systems over time, and we do need backup systems ready to go in case of a failure. We've recently seen things in the news about, and you may have experienced, a hospital that might have had a challenge and data compromised. You may have gotten a notice from one of these companies that says, hey, your data's been compromised. Or you may even go to a hospital and you may have experienced a case where you have to avoid certain locations because they've been under attack and now they're reduced to sending paper labs around. And the cost of that in terms of life and convenience is very, very high. These targets are very valuable, and that's not the only threat. We also are now facing a new threat with quantum computers. Quantum computers are coming at some point that will be able to break our best algorithms for public exchange of private information. But are these systems safe today? What about encrypted hard drives? Are they safe? The challenge that we face with quantum is impacting what's known as asymmetric cryptography. Now, this is a process that's very complicated, and the math involved is very intense. It fundamentally, at a high level, involves understanding that these functions are one-way in nature. One-way functions are functions that are designed to be difficult to compute in one direction, but easy to verify in another direction. Now, we're not going to go into all those details because it is so complicated that we need a lot of coffee in the room to stay awake for it. But suffice to say that these things are out there and that the threat from these algorithms will grow over time. We'll talk about the timeline for that in just a minute, but most experts believe it's still a ways out. And what about our other algorithms like symmetric cryptography? Things that protect our hard drives and our data at rest. When we protect them with AES security, those algorithms are considered safe, for now, that we know of. But the recommendation is to go to the next higher bit length. And that brings up a really good point. Security is an ever-evolving issue, right? Things that we do today, that we know about today, will be different in the future, and will have to evolve as we go. So it's important to consider the timeline. The timeline of these threats look like they're pretty far out in time, right? If we look at the slide here, it says that 2035 is the target for mitigating the risk. And we would think that's really far out there. But we need to make systems now that are hard enough to break, or that are hard enough to protect these systems so that it becomes economically infeasible in the future to hack into these systems and steal the data. We need to consider the timeline that these assets will be valuable. So things like national security secrets, for example, have a very long timeline that they need to be protected. Other assets that we have may be shorter in time. Nothing is secure forever, and the challenge is to make sure that it is secure over the life that it's deployed. So if we think about how long it takes to deploy and develop systems, we can think about things like servers that take 18 months to develop a new server and then deploy it into the market. It might last in the market for, let's say, 4 to 7 years, depending on the use case. Now, 2035 is not too far away. This timeline is an amalgamation of what's come out from NIST in terms of standard organizations, from the NSA with CNSA 2.0, and a White House security memo. And again, it puts a nice goal out there for us to work towards. We need government organizations like this to provide mandates for the industry to work toward an objective. And of course, then our private sector can benefit as well because we'll utilize the same techniques and the same algorithms. So the first thing that we need is we need those standards to be ratified. The word from NIST is that they will be ratified this summer, and they have really cool names like crystals, dilithium, but I assure you they probably don't read like a Star Trek episode. We need continued evolution of these standards, and that evolution will happen as new threats emerge. Already, the formulation for the next standards, the next set of algorithms is underway, and we need that to continue. We also need to work together with industry organizations like Distributed Management Task Force and PCIe SIG. These bodies are there to ensure that when we deploy these systems, they'll work together and they'll interoperate. And then ultimately, we need in-customer demand. In-customer demand is what will ultimately drive the investment in new technology. If the end customer doesn't recognize the risk and put into their specifications and requirements that we have these levels of security, then we will be unable to justify the cost of the development. Every development in security comes with a cost. It comes with a cost in hardware, in firmware, in software, and in customer usage. We try to make these costs as low as possible, but they're not invisible. And it really is the end customers that will drive the demand. Often we see that end customers only ask for security when it's too late, when their name is already out there in the news, and then they end up on a slide at a conference showing what not to do, but by then it's too late. So let's look at a little bit deeper into the ingredients that are needed for AI/ML asset protection and really many other assets that are out there. So we start at a fundamental layer of hardware security. But I also want to say that before I get to the ingredients, I want to say that these ingredients will be there in the future, right? When we have quantum computers, the algorithms fundamentally underneath will change, but the ingredients will remain the same, and in fact, we'll see new ingredients added as we go along. So we'll start at the hardware layer with excellent security there, which starts our ability to secure other pieces. If you don't have those hardware layers of security at the base, it's like leaving your front door unlocked. Then we'll move up into secure boot and secure firmware update. We'll have things like data encryption and data protection for drives and storage devices and memory systems. We'll have things like key management and key rotation, the ability to invalidate keys if they go bad and rotate into a new key and not go back to the old one. We'll have new concepts like transfer of ownership that addresses the cost of implementing and deploying security across multiple vendors. And then we'll also have things like secure debug. I recently read a report about an attack that started with an unsecured debug port where they were able to read out the keys from a device and then use that information to attack other systems. So we'll go a little bit deeper into the hardware root of trust. In the hardware root of trust, we use words like immutable. That means it can't change. Fundamentally, we want the base layer of security unchangeable so that we know what we deployed is going to be there and going to help protect us going forward. That layer is responsible for loading the first set of code from what's called mutable memory, and that's memory that can change. This is often data that's stored in flash, sitting next to the root of trust. That information is then validated by the hardware layer using keys that are stored securely in the device. And then we boot the rest of the system up through the layers to the operating system. So another key ingredient is attestation. So what is attestation? Attestation is the ability to get a security health status of your system. The platform root of trust is responsible to go read the status from every device that's plugged in. Was it securely booted? Is it running the correct firmware? Is it running the correct configuration? We can bring that back into a central location in the platform root of trust and verify all those components. Then we can also add a layer to that where we connect to that device remotely, and we can read its status. And we can know that every device that's on the network is running the correct code, the correct configuration, has the correct modules installed. These are the layers that we can use to help build automation, to make sure that a distributed network is safe and secure, even down to the lowest layers in the server. And now I'll hand it back over to Rob for the summary. Thank you.
Thanks, Cal. Thank you, Cal. All right, so let me wrap this up. We've got a couple of minutes here. So as Kyle discussed and I discussed in this presentation, we really have a few critical attack vectors that we're concerned about. Cyber attacks, physical attacks, and supply chain attacks. And we really were more ordered in on the physical and the supply chain. The quantum threat is real, as Kyle said. We have some time. There is the clock is definitely ticking, and it's really a call to action now for us as an industry to address the security needs that we're going to need in the future. And then hardware root of trust is the foundation. And as Kyle said, and as I mentioned in one of the very first slides, we need a distributed approach. All the ingredients have to be protected. As Kyle said, we can't have a Fort Knox approach. So that's really the key for this, is we need distributed protection of many ingredients. And the only booth number to remember for this entire show is 419, because that's where you're going to see the hardware root of trust demonstration from our 5th generation NVMe SSD controller. There's also a machine learning engine embedded in that controller where we have a demo on some use models that will improve performance and save power. We also have some other demonstrations around CXL with one of our great partners, Micron. We really appreciate them. Thank you, Micron. And then we also have our optical demonstration on PCIe Gen 5. So with that, I would like to say thank you very much for your time and enjoy the show.